start typing the word and it shows like a, is it like autocorrect?
Okay. All right. We're getting started.
All right, hello. Can you guys hear me in the back? All right, hi. Welcome to Data 8, Lecture 36. Today we have classifiers and a special guest, Professor John De Niro. Hello. I'm going to do announcements first and then hand it over to Professor. So I want to let you guys know that Jupyter Hub, unfortunately, will be down this Saturday. It is actually, I think, also down now, but for unforeseen circumstances. This time we know that when it's going to be down. So it's going to be down Saturday because they're doing construction at the building that the Jupyter Hub servers are on. So just be aware of that. It'll be down, hopefully not for the entire day, but you should probably plan for it just to be down the whole day, just in case it actually is down. The good news is we gave you an extra day to finish your project 3. So instead of having it due on Tuesday, it's due on Wednesday at midnight. Homework 7 was due yesterday. What else I got? So project 3, the checkpoint is due on Friday, and the entire project is due on Wednesday now instead of Tuesday because of the Jupyter Hub downtime on Saturday. Your final is going to be next Thursday from 2 to 5 p.m. We're going to be sending out room assignments in a bit. It looks like we are going to have the data lab rooms again for you guys, so just keep an eye out for an email about that. Instead of having a lab assignment next week, labs are going to be office hours where you can come in and work on final problems with your neighbor or with your TA. In addition, lectures on Monday, Tuesday, and Wednesday next week are planned to be final review, where we'll go over topics from the class and also work through some practice problems. All right, and without further ado, I'm going to introduce John De Niro. He used to work on translation at Google, but is now a professor here teaching 61A and Data 8. He'll be the professor for Data 8 in the fall. Here it is.
Cool. Oh, does this have a clip? I'm going to steal the clip from here.
Yeah, go ahead.
Maybe I'm not. Hang on, folks. That's okay. I'll manage. Think it'll work?
Yeah, I hope so.
I think it'll work. I'm pretty loud. Hi. So anyway, yeah, I'm John. Thanks for coming. We really designed this course as a new way to introduce people to randomness, statistical inference. I guess you're now deep enough in the course to have decided whether you like it or not. But this part of the course is something quite different from what people typically see in either a computer science or a statistics curriculum, which is building classifiers. Normally, machine learning topics are just saved until people are kind of deep into either a statistics or a CS curriculum. But there's no reason why you can't start learning about this stuff now. And I think it's a fun part of the course because the techniques you see here and the general problem setup of a prediction problem show up all over the place, both in industry and in academic settings. There's a lot of work like in health and also in the technology sector. It's just about trying to make predictions about what might happen. Basically, guessing the future of what would happen if you asked a person to do something. Maybe you don't need to ask that person because you can have it done automatically. So what else can I say? I'll go through the code today for a classifier. Your job in the project in this course that was just released is to build such a classifier. So I'm basically just telling you the answers to the project. You're welcome. But that's the right way to get started, is to see an example of how to build this fairly complex program. And then a lot of the project is about applying those ideas and kind of working with them and then understanding what comes out when you do. Oh, the mic's still there. OK. Any questions so far? Cool. So, I mean, all this stuff is in the textbook. So if you want to interrupt me with questions and ask about something, even if it's a little bit far afield from the stuff I'm talking about, I'm happy to answer that. So what's a classifier? This is a program that looks at some input, some representation of something in the world that's usually represented as a bunch of numbers, and then tries to guess some other attribute that you'd like to know. You looked at some examples last time, and I think you ended on a picture that looks something like this, which says that for each example, you want to classify it, and that means predicting some label for that example, like whether it's a spam email or a useful email. The classifier is this program, and this program is interesting because it's not just logic. It's kind of logic plus data. And the data is examples of labeled values that you've collected from the world. And the behavior of this classifier is not going to depend just on the code that you write, but also on the training examples that you give it to learn from. And this is kind of the standard feature of what's called machine learning, as opposed to just regular programming, is that you're writing programs where the behavior of those programs really depends on the data set that you give it. OK, now, in order to build this classifier, we need to select some data to use as a training set. And that training set starts with saying, what problem am I trying to solve? So if I'm trying to label emails as marketing or from my friend or whatever, then the label here is going to be friend or marketing. And the population will be the set of all emails that I might get. But typically, we don't see that whole population. We just see a sample. So you know this story from before. If we want to build a classifier, we not only need to see a sample of the inputs that we're going to apply it to, but also labels for each of those samples. So I've drawn this big box. But what I really mean here is that this is like a bunch of strips, a bunch of rows. And those rows tell me about one example, like one email. And there's a label corresponding to each row. I'm going to do something that you can appreciate because you know about randomness, you know about populations, but it's something that people tend to struggle with when they're first learning about classifiers, so pay attention. I'm going to take all of my labeled samples and I'm going to split them into these two sets. One I'm going to use to train the classifier, and one I'm just going to keep around until after the classifier is trained in order to figure out whether the classifier I learned is any good. And in particular, to get a sense of if I apply this classifier, which was just trained on my sample, to other elements in the population, how accurate might it be? How often might it predict the right label? OK, so what's the difference between the training set and the test set? The training set's used to model the association between attributes on the left side of the classifier and the labels on the right. Once I've come up with a story for how they're related, the attributes and the label, then I can use that in order to predict labels for new examples. And the reason I have a test set is to simulate what it's like to have new examples. So I use this test set to estimate the average accuracy of the classifier by trying to predict labels for each element in the test set and then seeing if I got them right or not because I have true labels. Doesn't matter what kind of classifier I'm building, and there's like a long list of different techniques for modeling the association between attributes and labels. You're still always going to have this setup where you split between training and test, and often this is just done randomly among all of the data that you have labeled. How are we doing? Questions so far? OK, so then we have to get specific. We have to say what kind of classifier are we going to use. You talked a lot about nearest neighbors last time, right? No? You never heard this before in your life. OK, so I don't know what happened last time, but I'll just start from scratch. There's this idea of what's called a nearest neighbor classifier. I'm sorry I've abbreviated it here, but if you look at the top of the slide, this is a name of a technique for modeling the relationship or the association between what you see in the attributes of an example and what you see as its label. And it uses a simple idea. It says, when you see a new example, something from the population, something from the test set, what you're going to do is find the most similar thing that you've ever seen in your training set before. And since that thing is similar in its attributes, we're going to hope that it's similar in its label as well. And so we'll just give it the label of the most similar thing that we've seen in the training set. So this is a procedure. This procedure says, I take some row from my population, just some example of some email. I look in my training set to find the most similar email where I know the label. And once I know the most similar example where I know the label, I just assume that this thing has the same label as this thing. Now, it's not always going to be right. Sometimes you have similar stuff with different labels. But usually, similar examples are going to have similar labels. I'm going to pause for a long time. That might squeeze a question out of you. How are we doing?
And what if we cannot find a similar
Great question. So what if you see an example that looks nothing like anything in your training set? There's really nothing you can do. It doesn't matter whether you're using this technique or another technique. You're really in trouble at that point. The right answer would be go find more data and get a bigger training set. OK, I think the way to make this concrete is to focus on a particular example. I'm going to take an example that someone else has already done before. There's something called the Google Science Fair. It's just like a Google-sponsored worldwide science fair where people submit projects. And the winner in 2012 was a 17-year-old named Brittany. And Brittany built a classifier as her science fair project. This classifier had a serious application. It was to look at images of cells and to predict whether that image was an image of some cells taken from a malignant tumor or from a benign tumor. So to indicate whether a person had breast cancer by looking at an image of some cells from their breast. And if you could do this, if you could classify this image, then you could go from just an image that a doctor can only understand to a label that a person could understand. Namely, does this person have a malignant tumor or not? Now, this is very serious stuff. Doctors can do this already. But there are cases in medicine right now where computers using classification techniques like this actually make better predictions from images than expert doctors do. So that's like one reason why this might matter. Another reason why this might matter is that there are only so many doctors in the world, and sometimes you have to wait a long time in order to get a doctor to look at your images. If you could get a classifier to run instantly, then that might be more useful to you. OK, so there's Brittany hanging out with someone you might recognize. This is what you get when you win the Google Science Fair. You can hang out. I don't know if you get to pick which president you hang out with or just the current one. But here's the kinds of things that this is supposed to classify. Here's an image. They take a slice of a tumor. They add some dye. You can see the individual cells. And individual cancerous cells look different than benign regular cells. And there's like a lot going on in both of these images. But you can see they're qualitatively different. And this is the label. So there's a step that Brittany didn't do, and we're not going to do either, which is to turn this image into a list of numbers. The way you turn this image into a list of numbers in practice in modern medicine, at least as it was practiced in 2012, was to get someone in a lab to describe this image. So instead of working on the raw image, we're going to work on properties of this image that are described by a lab technician or a doctor or whoever looks at this. And based on the properties of this image, like how big the cells are, and whether they all have this similar size or different sizes, and whether they have typical shapes or weird shapes, we're going to try to guess whether the ultimate label that this person should get is one of these two, malignant or benign. And we're going to assign numbers to each of those, which is just very common in classification. We're going to say benign is 0 and malignant is 1. And these classes or labels are the things we're trying to predict. And what's nice about Brittany's project is that her data set is published online, so we can just try it out. So we'll try to repeat her classification project. And if we can get 99% accuracy, then maybe we can meet Obama too. But we only have like an hour, so maybe we won't get that far. Questions before I jump to the data? Let's get to the data. Are you squinting in the back? Kind of bigger? Bigger? Bigger. How's that? This means bigger. Okay. This means good. Okay. I'll take it. All right. So here's a table. Each row describes a different image. Each value in each row is a number from 1 to 10 that describes what someone in a lab rated a certain attribute of the image. So we've gone from the original image to a different representation that does involve a human looking at it and doing things like measuring the uniformity of cell size. So this is like 1 means they're all uniform, and 10 means that there's some huge ones and some tiny ones. And then there are some that are a little more esoteric, and I don't even quite know what they mean. But finally, there's a column called class. And we can look at the distributions for some of these individual variables in the table. So here's the distribution across all the patients, of which there are 678 plus the 5 rows on the screen, so 683 patients. These are all measured on a scale from 1 to 10, and you can see like the clump thickness, which is the kind of thickness of different clumps in the image, varies all over the place. If you call hist with no arguments, it's going to draw a histogram of every single column. So let's just stare at the data for a second. You can see that for some of these attributes, like single epithelial cell size, there is some concentration. Like most of these are 2, and there are some that are bigger, but not too many. I don't even know what Blam chromatin is, I'm sorry. But you can see that most of this value is either 0 or 1 or 2, and then there are some examples that are 3, 4, 5. There's a bunch of 6s, etc. And then here's mitoses. Mitoses are almost all 1, meaning there aren't many. And then there's some few cases where there are more. There's that distribution of uniformity of cell size. And where's the one we looked at before? Here's clump thickness. And then what's really interesting is the class. So this is the class histogram. This means that 2/3 of the examples we're going to look at are benign, and 1/3 are malignant, 0 or 1. Any questions about the data? Good place to start with the problem is to look at the data, see what you're dealing with. Okay? Now, if we want to model the association between the attributes and the label, or the class, this histogram visualization maybe isn't the best one. What's the better one? We want to like look at the association between 2 variables. A scatter. Okay, let's try a scatter. I'm going to show you a slightly different scatter than you're used to. Since class is either always 0 or always 1, if you just do a a scatter between one of these values and the class, all the classes would be 0 or all the classes would be 1, and it's a little hard to see what's going on. So instead what I'm going to do is I'm going to scatter 2 different attributes. And I'm going to use the class to color the dots. OK, so everything in blue, benign. Everything in gold, malignant. And here's a scatter diagram of 2 of the many attributes where each dot is an example. It got its color from its class, and it's got its position just from these 2 attributes. And you can see stuff down in the lower left seems to be mostly class 0, and stuff in the upper right seems to be mostly class 1. Questions? Does this picture mean we can hope to classify using the attributes we have, or is totally hopeless? I guess what I'm asking is, do we think there's an association between the combination of these 2 attributes and this class, or not? Maybe, maybe not. Why don't you talk to the person next to you for a minute and come up with a yes or a no. All right. Here's what I might have come up with. I might have said something like, well, if bland chromatin is low and bare nuclei is low, then it looks like 0 is the right label. And if bland chromatin is high and bare nuclei is high, then it looks like 1 is the right label. And so there is an association between this pair and this class because they're different regions that have different colors. And I'm already describing a kind of classifier. You could write down this function, right? You could just say, like, check bland chromatin and bare nuclei, and if they're both low, then say 0, otherwise say 1. That would be a valid classifier too. We're going to try to build a classifier that runs automatically without you having to draw a picture or write any specialized code. And what's going on with these weird orange ones? Anyone know? Overlap. So there's actually 680 different examples here. Some of them actually have the same values for bland chromatin and bare nuclei, but different labels, different classes. So that's what you're seeing in these like grayish dots is that there's a blue dot and a yellow dot in the same place. So here's a visualization trick, which is to take each dot and just move it a little bit to the left or the right. Then they're not all overlapping each other. So I took each dot and I just randomly shifted it a little bit to the left, a little bit to the right, and a little bit up or a little bit down. So you can see that there's actually just tons and tons of examples that are 1, 2 on this scale of bland chromatin and single epithelial cell size. Oh, sorry, I changed values on you. This is some other attribute. But it has a similar pattern. And in this case, like, there's just tons and tons of these. So the reason this is a big dark square is that it's just like a bunch of dots that were randomly shifted around. But there are so many of them that they filled the whole space. And so this visualization, where we've jittered all of the dots, allows us to understand how many values are at each spot, instead of just seeing like a gray blob. And so you can see that there are some pairs of values for x and y that have the same value but the different labels. There's some blue dots here and some yellow dots here. That means classification looks hard, right? Everything I know about the attributes is the same, but the class or the label is different. So are we in like tons of trouble? Yeah, question.
Like in this case, go about like looking all of the attributes? Like if you know for sure it's 0 in this case, like the bottom corner, do you still look at the other attributes in the classifier, or do you just right away label it as 0?
Yeah, that's a great question. So there's lots of different classifiers one could imagine. People have even tried a technique exactly like you described. Like look at the reliable stuff first. If you can make a decision, make a decision. If not, then look at other stuff. That's called the decision tree classifier. We're not going to cover that exact thing in this class. But if you ever take another machine learning class, they'll talk about decision trees. You can also do pretty well by always looking at all the attributes. And it's just if one of them gives you a very clear signal, then it will kind of guide your prediction in a way that it effectively ignores everything else. But you raise another really good point, which is that in these cases where these two attributes don't tell you what to do because there's a bunch of yellows and blues mixed together, you really need to look at other attributes in order to make a decision. And then, so there's still some hope. Since we've only shown 2 of the attributes here and there are many more, maybe something else will tell us whether it's class 0 or class 1. OK. So how are we going to do it? We're going to do it by measuring the distance between examples. And the way we're going to measure distance is using our friend Pythagoras' theorem, which is that for each attribute, I look at the squared difference, I sum all those up, and I take the square root. So this is like the formula for the hypotenuse of a right triangle, but extended to many dimensions. That means that each example, each point, could actually have more than 2 values. It could have like 8 values. And what would I do? Well, I'd take the corresponding 8 values from another point, subtract them all, square each of those individually, take the sum of the squares, and then take the square root of that in order to get back into the original space. OK, so this is a distance formula. And there's some chance I have a slide which basically says the same thing in math. So let's take a look. I'm going to come back to that. So we don't use a lot of equations in this class, but if you have 2 different x's and y's, 2 different attributes, and you have 2 different examples, 0 and 1, then the way you'd measure the distance between those 2 examples is just to look at how they differ in one attribute and how they differ in another attribute. We square them so they're all positive, then we sum that together and take a square root. And this extends to 3 attributes or more attributes just by taking the difference between attribute values and squaring those. OK, so we have to somehow do this between rows in a table. Each row in a table is an example. We're going to look at 2 examples and figure out how different they are. So let me tell you a little bit about rows in a table. This is just like the code in the data science library for how you manipulate rows. Each row has all the data for some individual example. If you want the whole row, you take your table, you say which row you want, where I is some number, and now t.row I gives you a whole row. If you want just one value from that row, then you have to chain in this other method called item j, and that will give you a particular number. If you want to take the whole row and turn it into an array, then you call numpy's array function. What does this do? This takes any bunch of values and turns them into an array. The nice thing about putting them all in an array is then you could like subtract this array from that array and get the differences between all the corresponding values. And by the way, if you ever want to go through all the rows in the table, which we're going to do pretty soon, then you say for row in all the rows, t.rows, then you can get that row's particular item if you want. So this ... business is not real code, but it's just showing what you could do is you could refer to that row. When I actually get to doing this, I think maybe you'll have questions. But first, we're going to take attendance. And attendance should already be open. OK, cool. Here's a picture. Whoops, I missed. Everything okay with attendance? Okay, so let's say I had two different points. One's at 10, 10, and one's at 13, 14. The question is, what is the distance? The distance is the length of that line. Here's a function that computes it. All the row distance function does is turn both of these into arrays and then pass those into the distance function. So if I want to know what's the distance between something at 0, 0 and something at 3, 4, then it takes the difference between 3 and 0, squares it, that's 9. The difference between 4 and 0, that's 16, squares it. 9 plus 16 is 25, square root is 5. If I shift all of these up 10 and to the right by 10, the distance is the same. So here's a function that computes the length of that line. For posterity, here's a function that computes the length of that line. If I drop my mic, you'll let me know, right? Okay, one person will. Thank you. What happens if we have 3 different attributes instead of just 2? Well, let's take the easy example. So what's the difference between 0, 0, 0 and 3, 4, 12? We got difference between 3 and 0 is 9, 4 and 0 is another 16. So now we have 5 squared here, and we have 12 and 0, so there's 12 squared. It happens to be that if you have 5 squared plus 12 squared, you get 13 squared. So this is how it extends to multiple dimensions, multiple attributes. Even if I have 8 attributes, I can compute the distance. I saw some nods. I see not many hands in the air. Questions? Once we have distance, we have a plan. The plan is take a new example, compute its distance with every single example where we know the label, and then we can find the closest stuff. To find the k nearest neighbors of an example, according to their attributes, we find the distance between the example and each example in the training set. And then we take the set of all examples in the training set and we add another column, the distance column. That tells me the distance from the training set's examples to this one new example. Then we're just going to sort by distance. Now I know which ones are the closest. And we'll take the top k rows in order to find the k examples in the training set that are most similar to whatever example I care about. This is such like a precise specification that it translates almost directly into code. And this is what you're going to do in your project. Translate this into code. Here's the code. First, find the distances between each row in the training set and a particular example. Well, that's what this sentence says. I don't know why I said it. Okay, compute the distance from example for each row in the training. So what I'm going to do is I'm going to have a list of the distances. I'm going to take the training set and I'm going to get rid of the class. I don't care about the labels at this point. I only care about the attributes. I'm going to go through every row in the attributes of the training set. And I'm going to compute the row distance between that row, that training example, and the one example I really care about. And then I'm going to have my original training set, but I'm going to have one more column, the distance column, which tells me the distances to from each example in the training set to this example that I care about. And then I told you about this other part, closest. Closest means you get all the distances and you sort by distance, and then you take the top k. Patient at row index 12 comes into the doctor's office, wants to know, based on their image, are they sick? Image is taken, sent off to the lab. All of these values for all of these different attributes are entered by some lab technician, and we're given an example. That example is for someone where, let's pretend we don't know whether they're class 0 or class 1. So we've dropped that column, and then we've just taken this row. And what is this row? Well, this row is some value that is a container for all these different attributes. That 5 is that 5, and that 3 is that 3. OK, so this is what a row looks like. This thing isn't very useful. It's much more useful if we turn it into an array. Now we've just represented this image as just a bunch of numbers. OK? How much is all right? Now we're going to ask, who are the closest among the patients? We're going to leave out patient number 12. So among all the other patients, which one is most similar? What did I do? I forgot to execute this cell. Okay. Let's not exclude anyone for a minute. OK, so if we look in all the patients and see which one's most similar to patient 12, I would argue the most similar person to patient 12 is patient 12. OK? And so just like you'd expect, there's a row in here that's exactly the same as what we saw up here. And that's because of the same person, same example. If instead I'm interested in those that are similar but not the same, then I would exclude patient 12, look at all the other patients, and see what are the most similar patients to patient 12 that aren't patient 12. And now we see the most similar one has exactly the same clump thickness, 5 is 5. Exactly the same uniformity of cell size, 3 is 3. Exactly the same uniformity of cell shape, 3 is 3. Slightly different marginal adhesion, same single epithelial cell size, etc. So this is someone who almost looks the same, but isn't quite. The distance between this example and patient 12 is only 1.73. Is that small? Yeah, it's pretty small. It's smaller than all of the other patients. The next closest one is 3.16 away. And as you can see, all of these examples have a class associated with them. That's because in the training set, we know the classes, or we know the labels for each example. OK, so I've just shown you a little bit of code, and I've done the procedure that I said we were going to do, which is find the 3 nearest neighbors, or the 3 closest neighbors, by building this distances table and sorting it. Yes? Great question. So now we have like an important design problem, which is what do we do with these 3 nearest neighbors? We could just look at the nearest one of all and say the class is the class we're going to guess is the class for the very nearest neighbor. Another thing we could do is say I'm interested in 3 nearest neighbors and they all get a vote, and whichever class gets the most votes, that's what I'm going to guess. And that's the procedure for k nearest neighbors. So if k is 1, then you just take the class of the most similar example. If k is 3, then you look at all these 3 classes and you figure out which majority class, which one appears more than the rest. And that's the prediction you make. It turns out k nearest neighbors in many settings works a little bit better than just the one nearest neighbor. But it really depends on the data set. So the right thing to do is kind of try different values of k, like 1 or 3 or 5 or 7. Why am I picking odd numbers over and over again?
So you don't have a tie.
Yeah, it's just to avoid ties. It's convenience. So there's only 2 classes. If you have 3 examples, then one of those classes has to be the majority. So I know what to do in each case. Getting close, folks. OK, in order to classify a point, we find its k nearest neighbors. We take a majority vote among those k nearest neighbors to see which of the 2 classes appears most often. And we assign that example, that point, to the class that wins the majority vote. There's a couple more functions we need to write. We need to write majority class, which takes the top k and figures out which class shows up the most. Group by class, sort by the count, take the one that's at the top. What it means to classify is to just take the majority class of the closest k examples in the training set that are most similar to the example that I care about. So that means I should be able to classify using a training set that's all patients except for patient number 12. We pass in patient number 12 as the example. And if we use just one nearest neighbor, then what happens is we look in this table, find that the class of the nearest neighbor is 1, and that's the class that we guessed. And what we write? Well, here, we're finally going to look at patient number 12's class. It turns out that patient number 12 has class 1, and so the classifier is right. And what would happen if we use the 3 nearest neighbors? Well, it actually makes a different prediction. And this time it's wrong. So should you conclude that 3 nearest neighbors is garbage? No, not yet. Sometimes they'll be right, sometimes they'll be wrong. A good way to evaluate whether k of 1 is better than k of 3 is to try it over and over again and see on average how often is it right. So that's like the last step. It's usually when you define a classifier, it's some procedure, and it's got some numbers that you have to pick, like k in this case. And now we want to pick a good k. How will we pick a good k? Well, we have to have some data that's an example of the kind of stuff we'd get if we tried this out there in the wild on new examples from the population. That's what our test set is for. And whichever value of k behaves the best is the one we're going to go with. Uh-huh.
Does the value of k depend on the size of the population? Like which k would work best? Is that like
Great question. So is it about the size of the population? It might be, but the more typical thing is that it's about how much variability there is in the association between the attributes and the class. So if you get like a bunch of different classes for very similar values, the reason why you want a big k is to kind of average over all the stuff that's very similar so that you don't happen to care about something that's like right next to you versus not quite right next to you, but instead takes a majority vote among all the stuff that's very similar. So if you saw like an original picture, there were some that were like all blue except for like a couple of yellows. A large k will ensure that you guess blue whenever you're in that region, whereas a k of 1 might have you occasionally guess yellow because it happens to be very close to the yellow one. OK. So how do you solve your project? You write this, and then you write this. Each one of these functions does translate pretty well into English. Classifying means that you take the majority class of the closest examples. The last part we have to talk about is how you evaluate. So the accuracy of a classifier on labeled data is the proportion of examples that it got right. You know the right class, you know what it guessed, you just see what fraction you got right. So that means you need to compare the classifier predictions to the true labels, and if the label data set is sampled at random from a population, then what we can do is make inference about what the accuracy of this classifier would be on the whole population, even though we only looked at a sample. You could even draw confidence intervals and stuff like that. OK, so long ago I told you that we were going to take our data set, split it into training and test. We're going to use this to guess labels. We're going to use this to figure out whether our guesses were correct or not, and to compute the accuracy on the test set. So here's all the patients, 683 of them. We'll just split it in half. So the training set is randomly shuffled them. So I have no idea how the rest of this stuff in this lecture is going to come out. I randomly shuffled them. I took the first 342 and I called that the training set. I took the rest and called that the test set. And now we're going to compute evaluation accuracy on the training set and the test set by taking each example in the test set, so for I in the test rows, and classify that. So this is our guess about the label for that test example. And then we're going to check and see if what we guessed is the same as the truth. If we got it right, then num correct goes up by 1. So num correct starts at 0 and eventually will be the number of examples in the test set that we got correct. And the only part I've cut off is what happens to classify. Well, the way you classify is you take the test attributes, which is everything except for the class, and grab row I. So let's see how we did. Evaluate accuracy of the training set and the test set, where at first I'm going to say k equals 1. So I'll just find the most similar thing in the training set and use its label. This takes a while because we have to go through every example in the test set. And for each of those examples, we have to check every example in the training set. And then we got this weird number out, 0.9648. Is that good? Oh, that's the ratio of the number correct to the number of test rows. So that's our accuracy, not as a percentage, but as a proportion. To turn it into a percentage, we'd be 96.5% accurate. Apparently, we need 99% in order to win the Google Science Fair, but we got pretty close. How could we get closer? Well, what if we change this to 3? Whoa, 97.4% accurate. What if we change it to 5? 100%. No, I'm just kidding. It's not going to be 100% accurate. But, oh, we're up to 97.9% accurate. All right, let's try one more because I'm feeling lucky. OK, so does this mean that, OK, about the same. Well, and let's just get a little crazy and put 107 in here and see what happens. So eventually, if you look at too many nearest neighbors, you're just averaging among a bunch of stuff in the data set, and this might actually go down at some point. OK, so now we're back down to 95%. Even worse than if we just looked at 1. So I guess the story I'm trying to tell you is that we're attempting to estimate how accurate this training set classifier would be on the whole population by applying it to every element in the test set and then computing some average statistic. This doesn't tell us exactly how well this classifier will perform on the population. It's just an estimate based on a sample. The sample is the test set. But you know enough now to know that the sample's statistic is a pretty good indicator of what's going on in the population. This is the best way we can come up with, given the data we have, of evaluating whether this classifier is any good. And by trying out different classifiers, we can see which one generalizes better. I just used the word generalize. Let's see if I have time to explain it. Oh, I don't. OK, so maybe Sam will pick up and tell you a little bit about why we don't just evaluate accuracy on the training set, but instead use the test set next time. We're out of time. I'm going to hang out for a minute in case anyone wants to talk to me. But thanks a lot for listening to me. This was fun. OK, bye. If you have questions, just come on up. Give me like 5 seconds. I got to somehow stop my screen recording.